So you stumble across a viral post claiming 3I/Atlas just changed course, dimmed without warning, or split into fragments that defy known physics. The comment sections are ablaze with theories ranging from hidden moons to control maneuvers, and every new telescope image seems to fuel another round of speculation. But before we dive into what's actually unusual about this interstellar visitor, let's establish what strange really means in the context of comet science. Music started with the baseline behavior that every active comet displays. From the moment 3I/Atlas was discovered, astronomers expected the unexpected. Interstellar comets carry ices formed in alien solar systems, potentially with different volatile mixtures than our homegrown objects. When such a visitor encounters our sun's radiation for the first time, the outgassing patterns can be erratic. What looks strange to casual observers often registers as textbook behavior to planetary scientists. The challenge lies in separating genuine anomalies, deviations that demand new physics or revised models, from a natural chaos of a hyperactive nucleus responding to solar heating for the first time in millions of years. Take the brightness curve. In early October 2025, ground-based observatories recorded 3I/Atlas at magnitude 8.2, roughly on track with preliminary predictions based on its size and distance. Then, between October 15th and 18th, something shifted. Photometric data from multiple stations showed a sudden drop to magnitude 9.1, a change of nearly one full magnitude in just 72 hours. For context, a 1 magnitude drop means the comet appears about 2.5 times dimmer. Online forums erupted with claims of a shutdown or cloaking event, but the physics tells a different story. Dr. Elena Marchetti from a European Southern Observatory reviewed the light curve data in a preliminary report released October 22nd. Her team identified a sharp decline in production rate of cyanogen, one of the key molecules that fluoresces under sunlight and contributes to a comet's visible brightness. The drop coincided with a rotation of the nucleus, inferred from subtle periodic variations in the coma's shape. As a less active region of the surface turned toward the sun, the gas output plummeted. No mystery propulsion, no alien intervention, just the uneven distribution of volatile ices across a rotating, irregular body. This kind of rotational modulation isn't unique to 3I/Atlas. Comet 2I/Borisov, the previous interstellar visitor, displayed similar brightness swings tied to its spin. The difference here is the amplitude. Atlas's magnitude shifts are more pronounced, suggesting a nucleus with stark contrast between active jets and inert terrain. For researchers, this is fascinating, not frightening. It offers a rare glimpse into how interstellar ices weather under solar assault, but it doesn't require exotic explanations. Now let's address the tail, or rather, the lack of one. By late October, multiple imaging campaigns revealed that 3I/Atlas sports an unusually compact coma with minimal tail development. The dust tail, typically the most visually striking feature of comet, extends only about 20 arcseconds in process images, equivalent to roughly 300,000 kilometers at the comet's distance. For comparison, a typical comet at similar brightness might stretch several degrees across the sky. This stunted appearance has sparked countless theories, from electromagnetic containment fields to intentional suppression of debris. The reality is rooted in grain dynamics. Dr. Yuki Tanaka from Kyoto University's Department of Astronomy analyzed the dust size distribution using spectropolarimetry, a technique that measures how light scatters off particles in a coma. Her findings, published in a Rapid Communication on October 28th, show that 3I/Atlas is shedding unusually large grains, averaging 10 to 50 micrometers in diameter. These hefty particles don't respond strongly to solar radiation pressure, the force that normally pushes dust into a sweeping tail. Instead, they linger close to the nucleus, forming a dense, diffuse coma that barely extends beyond the immediate vicinity. Why such large grains? One hypothesis points to the comet's formation environment. If 3I/Atlas originated in a protoplanetary disk richer in refractory materials, silicates and organics that resist vaporization, its dust composition might naturally skew toward larger, more cohesive particles. Another possibility involves the current solar wind conditions. The October 21st coronal mass ejection didn't just deliver a magnetic shock. It also carried a burst of high-energy protons that can erode smaller grains through sputtering, leaving only the larger, more durable fragment behind. Either way, the short tail isn't evidence of anything unnatural. It's a signature of the comet's unique dust properties, shaped by its interstellar origins and the specific conditions it encountered near perihelion. For imaging enthusiasts disappointed by the lack of a spectacular tail, the consolation is this. The compact coma makes 3I/Atlas one of the best targets for studying dust grain physics in real time. Then, there's a trajectory question. Around November 1st, amateur astronomer networks noticed that 3I/Atlas appeared slightly off its predicted path. The discrepancy was small, just a few arcseconds in right ascension, but persistent across multiple observation nights. Within hours, social media lit up with claims of a course correction or power maneuver. Some posts compared the offset to speculative propulsion systems, citing science fiction concepts like ion drives or solar sails. The truth, as usual, is more mundane but no less interesting. Astrometry, the precise measurement of celestial positions, is tricky for active comets. The brightness centroid, the point that telescopes lock onto, doesn't always coincide with the nucleus itself. Asymmetric outgassing can shift the photocenter away from the true center of mass, creating an apparent positional error. For 3I/Atlas, the A1 and A2 non-gravitational parameters quantify this effect. JPL's latest orbital solution, published November 3rd, lists A1 at 1.9 times 10 AU/day superscript 2 and A2 at 8.3 times 10 AU/day superscript 2. These values are entirely consistent with a moderately active comet experiencing typical jet-induced thrust. Dr. Samantha Lawler, a dynamical astronomer at the University of Regina, ran Monte Carlo simulations to test whether the observed offset could arise from natural outgassing. Her results, shared via a preprint server on November 5th, show that even a single dominant jet, venting at a few hundred kilograms per second, can produce the measured positional shift. The key variable is the jet's orientation. If the active region sits near the nucleus's equator and the rotation axis is tilted relative to the orbital plane, the resulting thrust vector can push the comet slightly off the gravity-only trajectory. No propulsion system required. Just physics geometry and the chaotic dance of a spinning, venting iceberg hurtling through space. But what about the fragmentation rumors? On November 8th, a process image from the Las Cumbres Observatory Global Telescope network appeared to show a secondary condensation in the coma, roughly 5 arcseconds from the primary nucleus. The image went viral, with some claiming 3I/Atlas had deployed a smaller object or that it was breaking apart under unknown stresses. Within 48 hours, follow-up observations from other facilities failed to confirm the secondary feature. So what happened? Image processing artifacts are a constant hazard in comet astronomy. When stacking multiple exposures to boost signal, slight misalignments, or cosmic ray hits can create false features that look like real structure. The Las Cumbres team issued a clarification on November 10th, noting that the apparent condensation disappeared when they reprocessed the data with updated star subtraction algorithms. It was a ghost, not a fragment. Even if fragmentation were real, it wouldn't be unprecedented. Comets split for mundane reasons. Thermal stress cracks, volatile pockets erupting beneath the surface, or tidal forces during close solar approaches. 3I/Atlas's perihelion distance of $1.44 is far too large for tidal disruption, but thermal fracturing remains plausible. Dr. Nalin Samarasinha from the Planetary Science Institute has modeled the internal stresses in small, porous cometary nuclei. His work shows that rapid heating can generate pressure gradients strong enough to fracture weakly bound material, especially in objects with high porosity, above 70%. If 3I/Atlas does fragment in the coming months, it will be a valuable data point, not a mystery. Observing a breakup event in real time allows scientists to measure the nucleus's internal strength, composition, and structure, all parameters that are otherwise impossible to determine from a distance. Now, let's tackle the electromagnetic angle. Some online discussions have latched onto the idea that 3I/Atlas is surrounded by an unusual magnetic field, perhaps artificially generated. This stems from a misreading of plasma physics. All active comets interact with the solar wind, creating localized magnetic structures through processes like mass loading and ion pickup. The magnetic field strength near the nucleus can reach several tens to a few hundred nanotesla, depending on solar wind conditions and outgassing rates. Data from the Rosetta mission at Comet 67P provides a reference framework. During quiescent periods, Rosetta measured magnetic fields around 20 to 50 nanotesla. When a coronal mass ejection hit, the field spiked to 300 nanotesla, as discussed earlier. These spikes are transient, lasting hours to days, and are driven entirely by external solar wind dynamics. There's no need to invoke an internal magnetic field generated by the comet itself. For 3I/Atlas, no spacecraft is present to measure the magnetic environment directly. However, solar wind models and remote observations of the plasma tail, when visible, allow researchers to estimate the field strength. Preliminary models from the Space Weather Prediction Center suggest that during the October 21st CME event, the local field near 3I/Atlas could have reached 200 to 250 nanotesla. This is strong by cometary standards, but well within the range of natural solar wind interactions. No artificial field needed. The plasma tail, though faint, offers another clue. Observations from the SOHO coronagraph captured a brief disconnection event on October 26th, where a segment of the tail appeared to break away from the coma. Disconnection events are common during CME impacts. The sudden change in solar wind pressure and magnetic field topology can sever the connection between the tail and the nucleus, creating a dramatic but entirely natural phenomenon. For 3I/Atlas, the October 26 event aligns perfectly with the expected arrival time of the October 21st CME, reinforcing the interpretation that the comet's behavior is governed by standard plasma physics, not exotic mechanisms. Let's also address the spectroscopic anomalies. In late October, several amateur spectroscopists reported detecting emission lines that didn't match the usual suspects, CN, C2, C3, and OH. One report claimed to identify a line near 557.7 nanometers, coincidentally close to forbidden oxygen emission seen in Earth's aurora. This sparked speculation about atmospheric interactions, or even a breathable atmosphere around the comet. Dr. Michael Ahern, a leading expert in cometary spectroscopy at the University of Maryland, reviewed the amateur spectra. His assessment, shared in a blog post on November 2nd, pointed out that the 557.7 nanometer feature is likely a blend of two weaker lines, an H2 at 557.5 nanometers and a continuum contribution from scattered sunlight. The human eye and many amateur spectrographs struggle to resolve features separated by less than a nanometer. What appears as a single line is often a composite signal. Moreover, the oxygen line in question requires extremely low densities and specific excitation conditions to form. It's a hallmark of Earth's upper atmosphere, where oxygen atoms are sparse and collisions are rare. In a dense cometary coma, collision rates are high, and the forbidden line will be quenched, suppressed by collisional de-excitation, long before it could produce a detectable signal. The presence of an H2, ammonia radical, is far more consistent with cometary chemistry and poses no puzzle. As for the breathable atmosphere idea, it's worth noting that even the densest cometary comas have particle densities millions of times lower than Earth's atmosphere at sea level. A human standing on the surface of 3I/Atlas would experience near-vacuum conditions, with gas molecules so sparse that breathing would be impossible. The coma is visible from Earth only because sunlight fluoresces the molecules, not because there's enough gas to sustain life. So where does that leave us? As of mid-November 2025, 3I/Atlas remains on a predictable trajectory, dimming and brightening in response to its rotation, shedding large dust grains that form a compact coma, and interacting with the solar wind through well-understood plasma processes. The strangeness people perceive stems from a combination of factors: the comet's interstellar origin, which invites speculation, the dramatic but natural effects of the October 21st CME, and the limitations of amateur observations, where processing artifacts and misidentified spectral lines can fuel misconceptions. The real story of 3I/Atlas isn't about aliens or anomalies. It's about a small, irregularly shaped nucleus, probably half a kilometer across, carrying ices forged in another star's protoplanetary disk. It's about the physics of dust grains, plasma boundaries, and rotational dynamics playing out in real time under the harsh conditions of the inner solar system. It's about the hard work of astronomers and citizen scientists around the world, gathering data point by data point, refining models, and pushing back against premature conclusions. Music. In the coming months, as 3I/Atlas recedes from the sun and fades from view, the data collected during this apparition will be analyzed, peer-reviewed, and debated. New papers will emerge, refining estimates of the nucleus size, composition, and activity. Some questions will be answered. Others will remain open, awaiting the next interstellar visitor, or perhaps a future mission that can intercept such an object directly. For now, the lesson is clear. When something seems strange, the first step isn't a leap to extraordinary explanations. It's to ask, what do the data actually show? What are the uncertainties? What natural processes could account for the observations? More often than not, the universe's true behavior is strange enough without embellishment. 3I/Atlas is a reminder that interstellar visitors are not magical or artificial. They're laboratories for testing our understanding of cometary science under extreme and unfamiliar conditions. The strangeness isn't in the comet itself. It's in our willingness to see mysteries where there are only measurements waiting to be understood. Music. As December approaches, keep an eye on the sky, not for alien ships or impossible physics, but for the quiet, persistent glow of a traveler from beyond, slowly fading into the distance, leaving behind a trail of data and a challenge to explain it all with clarity, precision, and patience. That's the real adventure, and it's only just beginning.